A circular sanitary sewer is being designed to have a minimum velocity of 2.5 feet per second at peak flow. The sewer is made of cement mortar with a slope of 0.3%. What is the minimum diameter in inches required to meet the velocity requirements for this design? So, although the problem doesn't come right out and say it, we should be able to determine that we need to use Manning's equation for this problem. In water resources, Manning's equation is often used to find the flow in either a partially full or full pipe. If the pipe is full and under gravity flow conditions, this will be the peak flow and velocity of the pipe. Technically, the peak flow may occur slightly below the point where the pipe is full, but that's more of an in-the-weeds conversation outside of the scope of this problem. Anyway, some of the hints we can use to determine that we need to use Manning's include the following. So 1. The question provides the material of the pipe, which we can use to find the Manning n value. Second, the problem gives us the velocity and slope of the pipe, both of which are terms in one of Manning's forms. Finally, we are asked to find the diameter of the sewer, and area is also one of the terms within the hydraulic radius. So let's start by solving the problem. We are going to use the form of Manning's that only includes velocity. So if we search Manning's in the reference manual, it should lead us to page 345. That equation is going to be V equals 1.486 over N times hydraulic radius raised to the 2/3 slope square root. So let's plug in our givens below. We know that velocity is 2.5 feet per second, 1.486 over n. Now n we can look up in the reference manual on the next page, on page 346. And for cement mortar, we're going to have an n value of 0.013. Next, we can write out the expanded term of hydraulic radius, which is going to be the area over the wetted perimeter, raised to the 2/3, finally slope square root. As you can see, we need to expand the hydraulic radius into its constituent terms. So over here, we can do A over PW to the 2/3 equals pi d squared over 4 over pi d. So the area is still on the top and the wetted perimeter is still the terms on the bottom. And all of that is still to the 2/3. Simplifying this down, we get d over 4 to the 2/3, which we can finally simplify to d to the 2/3 over 2.52. Next, we can plug that back into Manning's equation. So step 4, 2.5 feet per second equals 1.486 over 0.013 d to the 2/3 over 2.52 times the square root of the slope. And slope we didn't talk about, but 0.3% can be written as 0.3 over 100 equals 0.003. So that's going to be over here expressed as a decimal. And what we can do at this point is solve for the diameter, which is what the problem asks for. So finally, we can break this down to, if we multiply these terms over here and then divide by 1.486 and the slope, we will get d to the 2/3 equals 1.006 feet. And solving just for d, we get 1.004, so that doesn't change much, feet, which of course is just about 12 inches. And that is all it takes to solve this problem. In summary, in this problem, we need to realize that we need Manning's equation, and we need to know where to get our Manning's n from. We also need to remember that slope should be expressed as a decimal, even if it is given as a percent. And that's it.